fluctuation response relations in non-equilibrium systems. Please.
Okay, so thank you for the introduction. And first of all, I'd like to thank the organizer, Professor Sanjib, for inviting me here. I mean, I love this place and I love this weather because not hot, not cold, but Korea is very now cold. And of course, I'm grateful for giving me this opportunity for sharing my work, to share my work with all the participants here. Okay, so today's my topic is about fluctuation response relation. So it sounds like a little bit old story, right? But however, in fact, it is a new challenge. So today I'm going to talk about fluctuation response relations in non-equilibrium system. So this is our main reference. So this movie shows Brownian particle in a bath. So here the large ball is a Brownian particle and small balls are bath particles. So what are the effects of the thermal bath? So first obvious one, it gives a stochastic motion or fluctuation of the particle. This stochastic motion or fluctuation originates from the interaction between the Brownian particle and bath particle. And second effect is dissipation. So for example, if we put a particle with initial velocity v0, then this velocity will decrease in time. This is also originate from the interaction between the particle and bath particles. And third important one is related to response to the perturbation. So let's say that this is the initial condition, the velocity equal to 0. Then if we apply some external force, then it will move in this direction with a certain velocity here. So this velocity is determined in this way. Here mu is a response or mobility, which is determined from the bath property. So for example, if bath is less dissipative, then the mobility will be higher and vice versa. So in such a way, these three effects have the same origin. So it means that there must be a relation between them. You know well about this. So indeed, in equilibrium, their mathematical relationship are well established. So this is one example. So this is a response, and it is given by the velocity-velocity fluctuation, and it is equal to the 1 over, this is a dissipation coefficient. In such a way, they are related. And this is a well-known Green-Kubo relation. That means mean current is given by this value. Here, L is a response to the perturbation F. And it is sometimes called Onsaga coefficient or Onsaga matrix. So this response is given by the current fluctuation. So here you can see that a response is linearly proportional to the fluctuation. Okay, so so the fluctuation response relation serves as a fundamental basis for understanding the dynamics of a complex system, and everyone knows well about the relationship in equilibrium. Then what about non-equilibrium? Not much is known compared to the equilibrium system. So there are a few previous studies about this non-equilibrium fluctuation response relation. So first famous one is a Harada-Sasa relation. So this is a relation between the dissipation and violation of the FDT. So in equilibrium, this fluctuation and this response, these two terms are the same. So this term vanishes, so there is no dissipation. However, in non-equilibrium, these two terms are not the same, so this term generates some dissipation. In this sense, this relation is very useful and meaningful. However, this Harada-Sasa relation does not give an explicit relation between the fluctuation and response. And we can write a more general expression for the response and fluctuation. So they studied this dynamics. This is a Fokker-Planck equation, and L0 is original dynamics, and L1 is perturbation. So in this system, we can write response in this way. However, this term is experimentally usually intractable. So, I mean, and then there must be a few more references. Here I met Anupam and we discussed about this fluctuation response relationship, and he mentioned that there are a series of papers by Christian Mais and Urna. To be honest, I didn't know that, so probably we can discuss it later. And then if you know some interesting papers about this topic, then please let me know after the talk. Okay, anyway, today I'll focus on my relation. Okay, so in this context, one important relation was found in this year. So this relation is called the fluctuation response relation. So it looks like this. Okay, so they considered Markov jump process. So they considered Markov jump process in the steady state. So here, J and J prime denotes a current-like observable. And here, Bij is some parameter, some perturbation parameter for edgy I and J. Here, I and J are indices for state I and J, respectively. So here, this term, partial derivative in terms of Bij, this one, is actually regarded as a response to the perturbation Bij. And this covariance between J and J prime is actually the fluctuation. So in this sense, this equality gives a fluctuation response relationship. And this equality holds only for infinite time limit. And from this relation, we can derive this inequality called response TUR. So it looks like TUR. So here, sigma dot is entropy production rate. So let's say that there is some parameter epsilon here. I will explain it later. So this partial derivative in terms of epsilon can be regarded as a response function to the perturbation of epsilon. And this variance is a fluctuation. So this inequality also gives us some relationship between the response and the fluctuation. Okay, so these two relations are important and interesting. However, as I mentioned, these two relations are limited to infinitely long observation time and current-like observable.
This is finite volume limit?
Sorry?
This is finite volume limit?
Finite volume. I mean, they are considering.
Is this true for any finite volume?
What do you mean by finite volume? They consider the Markov jump system for some specific network.
Number of edges or something?
No, it can be finite. I mean, it can be any number.
Any number?
Any number,
So
yeah.
you don't take any limit on that?
Not limit on the number of a state, but actually it works on for infinite time limit. Only for infinite time limit, not the number of edges.
What is IJ?
IJ is a state index.
Space.
State index.
I see.
Okay. Okay, so any other question? No? Okay, so they are limited to this long time limit and current-like observables. So we need to generalize this relationship to be applicable to finite observation time and arbitrary observables. Sorry? Covariance. I mean, this covariance is calculated in the steady state. And I will explain what is this perturbation a little bit later.
And these derivatives are computed with Bij 0, like in equilibrium case?
Not it should be 0, but it can be any number. But yeah, it can be any number, yeah. You will see what it is. Okay, so we succeeded in achieving this generalization finally. So we finally obtained this inequality called fluctuation response inequality. This is applicable to finite observation time and any observables. So from this relation, we found that by taking time goes to infinity limit, this inequality becomes equality. So this is a previous result I showed you, a fluctuation response relation. And here, by taking the equilibrium limit of this, then we can show that it goes to the well-known FDT. And let's go to the, this other branch here. So we can derive response thermodynamic kinetic uncertainty relation, or shortly RTKUR, from this FRI. And from this relation, we can derive well-known TUR and KUR. So in that sense, this hierarchical structure shows us that even though these well-known theories, FDT, TUR, and KUR, even though they look different, but they have the same origin, which is a fluctuation response inequality we have found. Okay, in this sense, this hierarchical structure, I think it is important in theoretical aspect. So we studied this classical system first, and then we extend this theory to the open quantum system. So we found the quantum fluctuation response inequality. So these are our whole story today I'm going to talk about. Okay? Okay, so let me first talk about our setup. We considered continuous time Markov jump process. So this is a master equation. So here, let's say that the pi denotes a steady state probability. Then this is a transition rate, Wij. And this can be parameterized by two terms. First term is Bij. Bij is a symmetric part, which means that Bij and Bji, they are same. And the second term is Fij. Fij is antisymmetric part. So Fij is equal to minus Fji. I don't know why. Okay, probably there is some connection problem here. Okay. So, and this is an expression for observable theta. So here, this is the most general form of observable. Here, h function is a delta function. So st denotes the state of the system at time t. So when the system is in state I at time t, then this function becomes 1, otherwise 0. In such a way, it can measure this, the state of the system. And here, Nij is accumulated number of jumps from state j to state I. Okay, so for example, if g equal to 0, then this term vanishes, only this term remains. Then n lambda ij equal to minus lambda ji, then the remaining this observable becomes a current-like observable. And if this lambda ji equal to 0, then this term vanishes, and only this term remains, then this theta becomes a state-dependent observable. In such a way, this is a very general form of observable. So within this setup, there are two ways of perturbing Wij. So first way is perturbing Bij. The second way is perturbing Fij. So first perturbation is called kinetic perturbation. Second perturbation is called entropic perturbation. So let me first talk about what is kinetic perturbation. Kinetic perturbation means that we change Bij into this Bij plus delta. Delta is a small number. So then this change leads to this change of transition rate. Wij, Wji, actually they are the same. So there is some additional factor here, same factor here. So this perturbation is like if there is a state I and state j, and this perturbation is like a perturbing energy barrier between them. So this plus delta means that decreasing energy barrier as much as delta. So what is the effect of this kinetic perturbation in equilibrium? So in equilibrium, detailed balance condition is satisfied. And if we do this kinetic perturbation, then this Wij, Wji changes in this way. But even though this transition rate changes, but the same equilibrium state actually satisfies the detailed balance. That means even though we do this big perturbation in equilibrium, steady state, equilibrium steady state does not change. and observable does not change. So there is no response to this B perturbation in equilibrium. So only kinetic properties varies. That's why the name is kinetic perturbation. Sorry? External? Where's it? The first time. This one? Yeah, this one. Okay, here. Oh, epsilon. Okay, so I will sorry, I will explain it later. But here we will assume that all Bij is a function of epsilon. I will introduce this epsilon a little bit later. So, okay, you will see. You will see. Sorry. Okay, any other questions? Okay. So the B perturbation does not change anything. Only kinetic properties vary. So we actually traditionally, we have not considered this B perturbation in equilibrium. However, in non-equilibrium, this B perturbation changes the steady state and observable. So it gives a non-zero response. So we have to consider this B perturbation in non-equilibrium. Okay, then what is the entropic perturbation? So this is entropic perturbation. So it leads to this change of transition rate. Here, actually, these two factors are different. This is a positive and this is a negative. So this is like a tilting energy barrier. So here, I state energy is increasing, and this so J state energy increasing, and I energy is decreasing, something like that. So it is like applying a driving force. So this F perturbation drives the system out of equilibrium. So entropy is produced. That is the reason why we call this entropic perturbation. Okay, so this F perturbation changes the steady state and current, so it leads to a non-zero response. So we have to consider this F perturbation in non-equilibrium response theory. Okay, so for these two perturbations, now let's talk about response to these perturbations. Okay, so this is an observable expression. Here we can define this integrand as an observable rate, theta dot. Then this is a protocol of a perturbing alpha. Here alpha can be either Bij or Fij. So this is a perturbation protocol in my mind. So initially, the system is in the steady state with a certain value of alpha 0. It should not be 0. It can be any value. It can be any, the finite value. Okay, so because it is in the steady state, this observable rate will be some constant value, initially constant value for negative time here. And at time t equal to 0 here, then we perturb this alpha in this way, alpha 0 to alpha 0 plus delta. And we retain this perturbed value for positive time. Then the system will relaxes to a new steady state, right? So this is a new steady state value. So within this protocol, we can define one type of response in this way. This is called static response because we need to know two steady state values here. So first value is, this is a steady state value in the perturbed dynamics, and this is a steady state value for the original dynamics. So this static response can be obtained from infinite time measurement, right? Because we have to wait for this infinite time to attain this final steady state value. Okay, so at this stage, let me go back to the previous result. This is a fluctuation response relation found in this year. Here they actually they employed this J is a current-like observable. So it means that they set G equal to 0 and lambda ij minus lambda ji. So the remaining observable is this is a current-like observable. So if we define this J, then actually they use this J here. So they use this current-like observable. Here, actually they use this response, actually they use this static response. So when they calculate this response, we need to know these two steady state value. So because this static response can be obtained from infinite time measurement, so that's why this equality holds only for infinite time limit, okay? Okay, so to numerical, okay, sorry. No, okay, sorry. So to numerically check this relationship, then we can first we can rearrange this inequality in this way. So by moving this term to the left-hand side, then we can define this Q factor in this way. And then if this inequality holds, then this Q factor should be always smaller than 1. So they evaluated this Q factor for various Markov jump network with various parameters. So these are the results. Every single data point represents the evaluated Q value for each network. So you can see that this Q factor is always smaller than 1. So it means that, okay, sir. Sorry, Bmax. I'll explain later. So yeah, it's some kind of a detail. So I will explain later. Okay, so so it means that every point is under this bound 1. So this inequality holds. And then the next question naturally arises is like this. Can this, this is an infinite time limit. This inequality holds only for infinite time limit. So we want to extend this inequality to finite time version. So for doing this, we can simply write the finite time version of this inequality in this way. This is not derivation, but simple, that we just write the finite time version of this one. And then we can first check numerically whether this inequality holds or not. So we did it. And this is a numerical check of this inequality, and this is a bound 1. But you can see that there are some violation point here. So that means that this simple extension is not valid. So how can we generalize this relation to a finite time version? So for this extension, we have to define another type of response, which is called dynamic response. As I mentioned, static response only can obtain from infinite time measurement. However, dynamic response, we can obtain this one from finite time measurement. So for obtaining this, we first we choose one finite time tau here. And this is actually in the middle of the relaxation process. So this is finite time. And here we calculate this mean value of observable for this perturbed dynamics. And this is a mean value of observable for the original dynamics. So in this sense, we can calculate this dynamic response from finite time measurement. And because this is a finite time measurement, then we can actually extend the theory to the finite time version. And this is a relation between these two. Okay, so using this dynamic response, we can derive fluctuation response inequality. If you are familiar with TUR and KUR, then you may know this TUR and KUR can be derived from Cramér-Rao inequality with a single perturbation parameter. However, in our setup, there are multiple perturbation parameters. There are many Bij, many Fij. So we have to use Cramér-Rao inequality with multiple perturbation parameters. And this is a formula. The formula is given by this matrix formula. So it is a little bit complicated to calculate. So here, R alpha denotes a dynamic response, and here this I matrix denotes a Fisher information matrix, and this is a variance of observable. And this is actually non-trivial to calculate this one. However, for example, if we first consider B perturbation, so here alpha is a Bij, in this case, by choosing this dynamic response, then we can show that this Fisher information matrix becomes a diagonal matrix. In this, a very simple, I mean, the calculation is not simple, but anyway, it becomes a very simple diagonal matrix. So we can easily calculate this matrix. So it simply reduces to in this way. It becomes a square and divided by this number. So this is the first FRI. And the second one is if we consider F perturbation, this Fisher information matrix also becomes a diagonal matrix. So we can reduce this matrix calculation in this way. So now we have two FRIs. So these FRIs are valid for finite time observation and arbitrary observable. So we can numerically check this inequality. So same way, we can, by moving this variance to the left-hand side, we can define this Q factor. Then Q factor should be smaller than 1. So we explicitly evaluate this Q factor for various networks with various parameters. And you see that all data points are below this bound 1. And we also check this, numerically check this inequality. So all Q factor, evaluated Q factor is below this line 1. So these two inequality really holds for any finite time tau, okay? And additionally, we found one more relationship between B response and F response. So this is a B response and this is F response. They are not independent, but they are related in this way. So by using this relation, we convert this inequality to this inequality. So you see that there is that we convert this F response by using this relationship. We change this F response to B response in this way. Why we did this? Because to compare our result with the previous result. So here in the previous result, if we set J equal to J prime, then this becomes square and this covariance becomes variance. Then if we look at these two inequality and equality, then actually they look very similar, right? But essential difference is that we employed dynamic response, but they use static response. Okay, so let me numerically check whether this inequality holds or not. So we can define this Q factor, and then we explicitly evaluate this Q factor, and this is the numerical result. And you see that all the data points are below this one line, so it satisfies for any time. Here we use the current-like observable. And there is one interesting point here. If we look at this regime, this is a large time regime. Then all data points collapses to the bound here. So that means even though this is inequality, but for large time limit, this inequality goes to equality. Actually, this is actually the consistent with the previous result. This is equality holds for infinite time limit. That means our bound, our inequality goes to equality in the large time limit, consistent result. And we also found one more interesting point here. So for small time limit, also this inequality becomes equality, okay? So far, I've talked about the fluctuation response inequality, and this inequality becomes equality in the infinite time limit. And then now let me talk about then how we can derive this RTKUR from FRI. Okay, so this is a fluctuation response inequality we found. And this is a transition rate, Wij. Here, let's say that all Bij is a function of epsilon, your question. So let's say that all Bij is a function of epsilon, which means that we can control Bij by adjusting some parameter epsilon, okay? And then in the same way, let's say that all Fij is a function of eta. That means we can control all Fij by controlling eta parameter. Okay, then we can, for example, define this response function to the perturbation epsilon. So by perturbing epsilon, we can measure this response. Then this is nothing but the chain rule. So here we define Bij is Bij equal to this one. So this is a partial derivative in terms of epsilon. And then we will use this Cauchy-Schwarz inequality. And here, by moving this term to the right-hand side, we have this inequality. So we will use this inequality. So here, by setting x and y in this way, and just simply putting this equation to this inequality, then we have this inequality. And this numerator is nothing but r epsilon. So this is r epsilon square. And let's say that there are many Bij, but let's say that B max is a maximum value of this among this Bij. Then we can take this number out of this summation. So then this number is smaller than this number. This is the definition of a B max, okay? And this red colored text is actually the definition of a pseudo entropy production rate. I mean, this is just a simple definition. So by comparing these two, we can write inequality in this way. And by comparing these two, then we finally have this inequality. And one more information here. So pseudo entropy production is always smaller than total entropy production and 2 times of total dynamical activity. So finally, we have this response thermodynamic kinetic uncertainty relation. So we have now this inequality. So let's compare our result and the previous RTOR. Then this is actually valid only for infinite time and current like observable. But this inequality, even though they look the same, but this inequality is valid for any time and any observables. Okay, so I've talked about this RTKOR can be derived from FRI by using Cauchy-Schwarz inequality. And the next thing is I want to show you TOR and KOR can be derived from RTKOR. Okay, so this is RTKOR. Here I will consider uniform perturbation. The meaning of the uniform perturbation is that all Bij is the same as B. So B max is also same as B. Under this perturbation, we can show that this response to the perturbation epsilon can be written in this way. B times the mean value of observable. Then if we plug this equation to this inequality, then we can easily get this thermodynamic or kinetic uncertainty relation. So for example, if we choose this sigma total entropy production, it becomes TOR. And if we choose this total dynamical activity, it becomes KUR. Okay, so I showed you that TOR and KUR can be derived from this RTKUR. Finally, I want to address this point. So the fluctuation dissipation theorem can be derived from FRR if we take equilibrium limits. Okay, so this is a fluctuation response relation. And if we set J is equal to J prime, that means, two observables are the same. Then this covariance becomes variance, and this becomes square. So this one is fluctuation, and this one is response. So their relationship. But isn't it look a little bit weird? Because in equilibrium, fluctuation is linearly proportional to response, but this equality shows us that fluctuation is proportional to response square. So that is what I mean by this equality looks a little bit weird. However, we can show that this equality reduces to the well-known FDT in the equilibrium limit. So let me briefly show you how to derive this one. So for doing this, let me first define empirical edge current, small jij. And actually, the mean value of this empirical edge current becomes a well-known capital Jij here. And here, let's define this matrix L. And this is a response, actually edge response. It denotes how Ji responds to external driving F and M perturbation. And this is actually the Onsaga matrix for empirical edge current. And the third one is we define this C matrix. C matrix is a covariance matrix of this empirical edge current. Okay, so now we define all things. And I will, skip all the details. This calculation is quite complicated. But we can show that from this equality, the left-hand side, variance J, we can show that variance J can be expressed in terms of this C matrix. Here, lambda is a vector, which is the weight Onsaga matrix here. So this equality holds for arbitrary lambda. That means this C matrix and this 2L matrix, they should be the same. So actually, this is a fluctuation, and this is So this is a fluctuation, and this is a response. So this is a fluctuation dissipation theorem in equilibrium. In such a way, so we can show that FRR goes to FDT in equilibrium limit. Okay, so I showed you this hierarchical structure between the theories, and then let me move on to the quantum system case. So we can extend this theory to the open quantum system. So this is our open quantum system setup. We consider the Lindeblad master equation system. So here, LK is a jump operator, and here capital K denotes a number of a jump operator. And this jump operator is parameterized by this theta k in this way. And this is an expression for observable. And the protocol of perturbing this theta k is the same as the classical case. So initially, the system is in the steady state with a certain value of theta k. And here, at time t equal to 0, we perturb theta k to theta k plus delta, and we retain this perturbed number for positive time. And then the system will relaxes to a new steady state. So the perturbation protocol is the same as the classical one. Then we can derive the quantum fluctuation response inequality using the quantum Craméral inequality with multiple perturbation parameters. So this is given by this matrix form. This is actually the same as the previous one. So this is R theta denotes a dynamic response, and this IQ denotes a quantum Fisher information matrix. And it is non-trivial to calculate this quantum Fisher information matrix, so I will skip all the details. But luckily, fortunately, we can show that this quantum Fisher information matrix becomes a diagonal matrix, same as the classical case. And here A is a traffic. Because now it becomes a diagonal matrix, so we can easily calculate this matrix. So it simply reduces to this simple inequality. So this is a quantum fluctuation response inequality. We found actually that this is the same form as a classical case. Okay, so from this quantum FRI by using Cauchy-Schwarz inequality, then we can derive this quantum RKUR. Okay, and then we can numerically check this inequality by defining this Q factor. We numerically test this quantum FRI for various models, 2-state model, 3-state model, and the number of jump operator, 1, 2, 3, 4, something like that for various models. So you see that all the data points are well below this bound 1. But there is one difference from the classical case. So in the classical case, as I mentioned, for large time limit, all data point collapses to a bound 1. That means large time limit, this inequality goes to equality in the classical case. However, in the quantum case, actually, we don't see such a behavior. So actually, this inequality does not go to equality even in the large time limit. This is a difference. Okay, so I talked about this whole story. Okay, so the main message is this hierarchical structure is telling us that this FDT and TUR and KUR, this kind of theories actually have the same origin. And this is what we have found, FRI. And we extend this theory to the open quantum system. So we also found the quantum fluctuation response inequality. Okay, so these are my collaborators. He's Professor Hyung-Kyu Park. Many of you know him. He is, in principle, retired 4 years ago, but after that, he took a new position, distinguished professor at KIAS. So he is still working with me. And he's a Dr. Hyun-Myung Chan. He's my postdoc. And this is a PhD student, Ui-jun Kwan. He's a student of Yongju here, Seoul National University. Okay, so thank you for your attention.
Thank you very much. For a very interesting talk. I guess we have time for 1 or 2 short questions, please. Yes. Mm-hmm.
So, are you familiar
No,
with
you have to use the microphone.
Einstein relation, are you familiar with it?
Sorry?
Einstein relation.
Einstein relation.
So can you derive using your formalism? I don't see it.
Okay, so I showed you the FDT can be derived from the FRR, but it is a relation for Markov jump process. So so the Einstein relation we can derive from, for example, usually derived from Langevin dynamics. So actually, we also studied Langevin dynamics. So in that case, we can derive such a FDT. But here, the not clearly seen such a Einstein relation in this derivation. But we can do it in the Langevin dynamics. Yeah.
Okay, Kasamasa.
Oh, two mics, okay.
Yeah, thanks a lot. I'm curious about the last part you mentioned. About for quantum case.
Quantum case.
The value doesn't go to 1, right? And what is the intuition behind it? How can I understand it? So basically, more specifically, is this because of somehow the observable is different, or? And also, can you think about the semi-classical limit?
Oh, sorry. So your question, okay. So
the last slide, FRI.
So, you mean that the collapses to bound 1 in classical system, but in quantum system they does not collapse to bound 1. So that's you mean?
Maybe in the last.
Okay. So
maybe next.
This is classical, yeah. I guess the quantum was at the very end.
Yeah.
Sorry. Okay.
That one, quantum FRI. Yes.
Okay.
So you said it doesn't go to 1, unlike classical case.
Yeah. Right.
Yeah. So what is the intuition behind it?
Actually, this is also. We are also curious about. We actually, to be honest, we don't understand. In that case, why they do not collapse to bound 1. So we are still in studying, investigating. For example, there is another kind of a fluctuation response relation to collapses to bound 1, but actually we have not found such a behavior. So actually we don't now understand the mechanism why they don't collapses to boundary one now.
In your framework, can you take the semi-classical limit?
What do you mean by chemical?
Or if you have something like Planck constant, for example, can you send it to zero? And
I mean, what we have used is only a Lindeblad equation, master equation. So, I mean, but not other things. So, yeah. Okay.
okay, thank you very much.
Okay, very good. So let's thank the speaker again. And let's have a coffee break, and we meet 11:30. No, this was a very nice talk. So I have, I mean, just one. Well, I want to say something about the Lindblad, but you know, there's one.